2 days ago, we took a look at how we charge objects by conduction and induction. One of these ways, conduction or induction, you tell me which one it is kind of the never way of charging. What do we mean by that? It never involves a charge transfer, and it never involves touching. Which one would that be? That would be induction, yeah. Induction never involves a charge transfer. Induction never involves two objects touching each other. Now, we put a little asterisk beside that because within induction, sometimes there actually is a charge transfer taking place, but not, and this is the important part, not between the object doing the charging and the object getting charged. Okay, and I'll explain that a little bit closer when I draw the diagram for that. Now, conduction is the other way we charge objects. Conduction doesn't always involve two objects touching, but it usually does, and it does always involve a charge transfer from one object to another. So, if you get the object doing the charging, transferring charge, it's got to be conduction. If you get two objects touching each other, it's got to be conduction. If you get two objects not touching each other, it's probably induction, but it still could be conduction, because conduction doesn't always involve a charge transfer. We break conduction down into two subcategories, friction and contact, which we sometimes just call conduction. Friction involves rubbing two things together. One thing is, if they're both neutral, and one becomes -5, the other becomes +5. If they're both neutral and one becomes +12, the other becomes -12. That's governed by the law of conservation of charge, right? If the total charge was 0, the total charge has to remain 0. So if one gains negative, the other has to lose negative and become neutral. Now, when we're charging by contact, we're either touching two things together, just like touching fingers together, or bringing them close enough together that it's like touching together. Lightning is an example of charging by contact. It's just that, I mean, it seems weird, right? Because lightning and the cloud and the ground aren't actually in contact with each other, but they're actually close enough on that scale, close enough to each other to actually transfer charge from one to the other. It's as if they're touching each other. They're not really, but it's as if they're touching each other. That's governed by the law of conservation of charge as well, right? If one of them is -5 and one of them is -7, once they touch each other, they're going to try to balance out to be -6 and -6. If one's 0 and one's +12, they're going to balance out to be +6 and +6. If they're conductors, right? If they're insulators, you don't get too much charge transferring, right? But if they're conductors and similar size, similar shape, they're going to try to balance out to be whatever, so that the total charge remains the same. Now, with induction, we have two separate categories of induction as well. One's called the temporary separation of charge, and one's called the permanent charge. We'll start with the temporary separation here, and this isn't new. We did it the other day. We start with a neutral object, and that neutral object can be any shape, right? I usually draw it as a circle, like as a sphere. It doesn't matter, whatever the shape. We bring another object nearby that's charged, let's say negatively charged. Doesn't matter what the shape of that one is either. And you know that when we bring a negatively charged object nearby, it doesn't mean it just has electrons. It's got both. It's got more electrons than protons. What happens to the protons in the neutral object here? Tanner? No. What happens to the protons in the neutral object, Alex? Nothing. The protons stay where they, I mean, I lie a little bit. Like, technically you're right. They are attracted toward that negative. They just don't move toward that negative, okay? So those positives are going to stay where they are. But Alex, those negatives aren't going to stay where they are they? What happens to them? Yeah, they're going to be repelled by the negatively charged object and go over to this side. So that leaves us with the separation of charge, we call it. One side is negative, and one side is positive. It's still overall, our object is still neutral, right? I get 3 positives, 3 negatives. It's just that they've separated so that one side is negative and one side is positive. Now, this is a bit of an oversimplification because you'd still have negative over here, but you just have more positive over here than negative and more negative over here than positive. Now, when we look at this picture, we see that the side of this object that is being charged the left side is negative, the right side is positive. The object that's doing the charging, that's this object right here, the thing that's doing the charging, the highlighted one, that's negative. The side that's closest to the charging highlighted object is opposite, right? We got positive right here, we have negative over here. That's why charged objects, negative, attract neutral objects right here, because the side that's closest to it becomes opposite to it. So you asked a question earlier about what's an application of this. Well, why do charged objects attract neutral things? Because in that neutral thing, you get a separation of charge that makes the side that's closest opposite, and opposites attract. Now, if I wanted to make this permanent, you guys saw the other day how to make this permanent, we attach a ground wire. It doesn't have to literally be a ground wire. It can be anything that is big enough to either provide electrons or be a sink of electrons to or from this object. It could be you, depending upon the size of the object that you're trying to ground here. But we'll draw it like this, as a wire that literally goes into the ground here. Now, it also doesn't matter where you put that ground wire. I'm drawing it on the far side, but if you put it over here or over here, it doesn't matter. You're going to get the exact same effect. The effect is this. The electrons in this neutral object want to be pushed as far away as they can from this highlighted negative object right here. Usually, as far away as they can go is the far side of the neutral object. But now, they can go down into the ground. That's farther. So that's what they do. These things that did go to the left-hand side now go down into the ground. Now we have a positive object. Now it's not neutral with a separation of charge. Now it's just charged. Charged positive, opposite to the thing that's doing the charging. If we cut that ground wire, then there's no way for the electrons to come back up from the ground. So this is now a permanently positively charged object. Does that make sense? So you want to charge something positive by induction. This is induction. Bring something that's negative nearby and then ground the neutral object. Okay? Now, some of you are going to look at this and say, well, wait a sec, there's charge transfer taking place there, right? Charges are being transferred down into the ground. That's true. That's conduction. But this thing isn't transferring, and this thing isn't touching. Because the thing that's doing the charging isn't transferring or touching, we still call the overall process conduction. How did this thing become positive? It lost electrons. It was charged by induction, even though conduction took place. It's still charged by induction. Yeah?
I'm just curious. So if you have a neutral object that becomes negative.
What about the other situation where we have a neutral object when we bring a positive object nearby? What happens to the protons now? They don't go anywhere. They stay where they are. What happens to the negatives? Well, these guys are going to get attracted now. So once again, we have a separation of charge. The left side is positive, and the right side is negative. Notice the right side negative is opposite to the thing that's doing the charging. Opposite to this thing. That's why charged object, positive, attracts neutral object, right? Because opposites attract. Now, if I attach a ground wire, or better yet, let's just attach some big oval thing, or almost looks like an eyeball. Attach some big eyeball to it. Well, it can serve as a ground, right? Just like the Earth serves as a ground. Why does the Earth allow electrons to transfer into it or out of it? Because it's so big. If you have some other big object, big relative to the thing that's neutral here, it doesn't matter if it's literally the Earth. Okay, the diagram that we see up here with the ground wire is the same as the diagram we see down here with this big eye, or whatever it is. In the end, this one would allow electrons to be pulled over from this into here, which gives us a net negative charge. Now, if we remove this big eye, before we take away the charging object, then it's going to remain negatively charged. It's now a permanent, semi-permanent, we call it permanent, negative charge. Does that make sense? We could have put that big thing over on this side. We could have put the ground wire up here. It doesn't matter. Okay, the big thing and the ground wire serve the same purpose, and it doesn't matter where we put them. It's going to accomplish the same thing. Okay, does that make sense? I want to show you a picture here of something called an electroscope. Okay, you haven't seen this before. This is a device. We actually have 10 of these in the back room, but they don't work at all. They're garbage. Maybe if we had spent some more money on them, instead of getting the cheapo ones, they would have worked, but these ones don't work. So there's no point in even pulling them out. But I'll tell you how they work. An electroscope is something that simply detects charge. It doesn't tell us what type of charge we have, positive, negative. It just tells us that we have charge, or not. Here's how it works. There's two diagrams of electroscopes here. They both end up being the same thing. There's a ball on the top of the electroscope. It's a conductor. There's a rod that's attached to that. It's a conductor. And then there's these two little foil leaves that hang down, straight down because of gravity. Really, really, really thin foil. Conductor still though. If I was to bring a negatively charged object nearby, what would happen? Well, remember that this thing is neutral to start off, right? With positives and negatives all over the place, balancing each other out. But if I bring a negative nearby, well, the protons are going to stay where they are in the electroscope, but the electrons, they're going to move. The electrons are going to move down into the leaves of the electroscope. They're going to be pushed away down into the leaves. What do you notice about those two leaves now? They have more negative and positive. They're like charged. They're going to repel, and they push each other apart. So the leaves of the electroscope become spread apart. We've just detected charge. Not that it's negative, just that there's charge in that object that we brought nearby. Let's bring another object nearby over here. Let's make it positive. Again, we have positives and negatives all over this thing. What happens to the protons? Nothing. What happens to the electrons? They're going to get pulled up, right? So we're going to pull these guys up. Not all of them up here, but lots of them up there. The ball of the electroscope becomes negative. The leaves become positive. What's going to happen to them as they're both positive? They repel and spread out. So we get the same effect in both situations, right? But one's because a negative was brought nearby, one's because a positive. We know that there was charge present in that object. We just don't know what kind of charge it was in that object.
Isn't it grounded though?
No, we're assuming that everything's insulated right now, but we will ground it in a second. Yep.
So if you were to touch the greater negative object with the ball, would that create more charge in there? So
If you were to what, sorry?
if you were to touch it, so
If you were to touch this with this?
That was the ball, yeah.
Yep.
Would it then, I guess, transfer charge
Yep.
and try to become neutral more or less?
No, this is neutral.
Become, I guess, simpler more or less.
Yes,
Yeah.
yes. So the electroscope is overall neutral, and this is negative. So if you touch those two things together, they wouldn't necessarily balance out perfectly, but you'd get negative and negative.
Yeah.
So the electroscope would become negative, and then these things would spread apart, and they would more or less stay spread apart because it's got a net negative charge then. What if we ground it, though? This kind of goes to what Eric was saying. What if we ground it? Doesn't matter what side we ground it on. It's kind of weird. Go ahead. Yes. Instead of moving down here, very good. Instead of moving down here, well, they want to move as far away as they can, right? Well, down into the leaves isn't as far away as they can go anymore, right? Down into the ground is as far away as they can go now. So electrons are going to go down there. So these leaves would still stay spread apart, but it wouldn't be because they became negative. It would be because they became positive. And if we cut that ground wire, well, now they're going to stay spread apart. Not permanently, but for a while, until they discharge with the air. Same thing over here, or similar over here at least. We catch a ground wire, it doesn't matter which side. We're not going to push negatives down into the ground, rather we're going to pull negatives up from the ground. This whole thing is going to become negative now, because we're getting a bunch of extra negatives in there from the ground. Or from whatever you touched it with, it's like the ground. Leaves spread apart, but not because they're positive, but now because they're negative. If I cut that ground wire or remove the ground, it's going to stay that way for a while, because there's no way for the electrons to go back where they came from.